Hey guys, F Train here. Hope everybody's doing well. um, it is currently Tuesday, and um, and we're going to be talking about neutron stars today. So let's get into it. All right. All right. So first of all, let's do a do now here. How might gravity waves or waves in space-time be created by an exploding supernova? So you might want to pause and think about that for a minute, and then recall that when we talked about type 2 supernova, we talked about this shock wave that happens as the iron core collapses. You have this sort of big bounce where you get it all the way down to the neutrons, and um, can't get any smaller. So you'll sort of get this great bounce, and all that energy coming from all that potential energy that was turned into, um, you know, nuclear energy and kinetic energy and all that all forms this huge shock wave. And it's actually, enough energy that it can actually causes ripples in space time. You may remember a few years ago, they had this thing called the LIGO detector, which actually for the first time discovered or detected gravity waves from a supernova. It was actually, I think, from the collision of two black holes, but basically it's the same idea. Okay, all right. So let's talk today. Let us talk today about, like I mentioned, we're going to talk about neutron stars. So, what remains of the star core after a type 2 supernova explosion? So that's what we're going to be talking about today. Um, so first of all, how are neutrinos formed in a supernova explosion? You should probably remember that when we have a massive star, we're talking like 8 to 20 times the mass of the sun. They cannot lose their mass rapidly enough, so they leave behind a nebula and a neutron star. Now, during the core collapse, uh, nuclei are broken apart. In other words, as the core collapses, you have this energy. It gets so hot and so energetic that basically the protons and the neutrons are just broken apart, and you have just this sea of protons and neutrons. And as they come back together, they'll form new types of new types of um, matter. It's called nucleosynthesis, and you basically that's where things like heavy elements like gold and everything are actually formed. Um, Pressure now in that core collapse, the pressure forces the electron and the protons together. And then you see here in this equation, if you take an electron and a proton, forms a neutron and a neutrino. Um, Neutrons are formed and neutrinos are released. So a lot of energy can be released in this form of neutrinos. Now, how can a neutron star support its weight? Well, neutrons are compressed to roughly the density of a nucleus. So in other words, during the core collapse, you have the neutrons, you have these protons and electrons forming neutrons, and you have so much gravity now that the neutrons are compressed rather to roughly the density of a nucleus, like 10 to the 14th grams per cubic centimeter. Um, so it's basically it's like an atom with no empty space. So imagine if you take an atom and you collapse all the electrons. It's basically like the nucleus of an atom. Okay. The neutron degeneracy pressure can support the weight of a neutron star, but only if its mass is anywhere between 1.4, that's the minimum mass, up to about 3 or I think exactly 3 solar masses, because as we'll see in one of our next lessons, if you get above 3 solar masses, then even the neutron degeneracy pressure cannot support. So normally, the strong nuclear force is an attractive force, but again, like we learned in a previous lesson, I think at this point it becomes a repulsive force, and it actually pushes the nuclei to get apart. Now, how big should a neutron star be? Well, if you think about it, if you know, let's say, for example, the mass of a neutron star, let's say the mass of the neutron star is 1.5 solar masses, to kind of put it in the middle there. And if you know its density is 10 to the 14th gram per cubic centimeter, you can actually do the math. And you could actually figure out that the radius of a neutron star that's 1.5 solar masses is only about 10 kilometers. So we're talking about the size of the island of Manhattan, or at least the diameter. That is really, really small when you consider it's 1.5 times the mass of the sun. Remember, the sun's mass is 300 or so thousand times the Earth's mass. So we're talking, like 500,000 Earths in the size of maybe Manhattan. How does a collapse of a star affect its temperature? Why can't it cool quickly? What type of energy should a black body emit if it has an extremely high temperature? All right, so why don't you pause and see if you can answer these questions. Okay, we're back. Oops, I can't see these questions because my thing's in the way here. Let me just pause for a second. Okay, so the surface temperature of a neutron star is millions of degrees Kelvin. At first, it cools very quickly, okay, because as the neutrinos are released, those neutrinos carry away a lot of energy. And there's literally bazillions of neutrons being released. So it cools quickly at first. However, eventually you've got this very, very, very small but very hot neutron star. And because its surface area is so small, we know that the energy is released as the rate of the energy release is a function of the surface area. We learned about that. We talked about flux and luminosity and things like that. So very, very small surface area. So therefore, it's going to cool very, very slowly. And it's so hot though that the black body radiation that it emits is in the X-ray portion of the spectrum. And the X-rays can cause the glowing of the interstellar medium. We talked about even how even white dwarfs can cause, interstellar medium to glow. Those are called emission nebulae. And so obviously X-rays can do the same thing. Neutron stars were first predicted back in 1934 by these gentlemen, Walter Bade and Fritz Zwicky at Caltech. However, they were not actually observed until 1967. Now, think about it. Why do you think they were so hard to see? And why do you think it took until 1967 to see them? Okay, think about what was going on in the world in the 60s. There was a race that was happening, which you may have heard about. And eventually, the United States won that race in 1969. So anyway, think about that. So anyway, this is, I'm sorry, Walter Bade and Fritz Zwicky. Now, the guy on the right there has a strong resemblance to a famous character. And if you're not familiar with that character, let me just show you a video real quick. There he is, right there. Remember that.
Detroit could take a lesson from this design. Here's Grandpa at the starting line. Oh! Hi, Grandpa! Oh, I'm so nervous. Eddie, stop biting your nail. We won! We won!
Okay, so anyway, if for those of you who are not familiar with Grandpa Munster, hopefully that will give you a little primer on the Munsters. One of the really quality TV shows from like the 60s and 70s. And I'm sure you can catch old episodes on, some sort of Netflix or YouTube or something like that. Okay. By the way, if you notice, Eddie was biting his nails. So, maybe your mother has told you in the past, like, don't bite your nails. Well, even back in those days, they had issues with that. All right. All right. So let's continue here. And so we're talking about why were they so hard to see, and a little, that show was from the 60s. So we see that why can't they be observed until 1967? And hopefully you were thinking about the fact that there was this race that was going on. It was called the space race. Okay, so we had the space race, and eventually, so where must an X-ray telescope be located? Well, we've talked about the fact that X-rays can't really penetrate the atmosphere, and so therefore, in order to see X-rays, which we said are being emitted by neutron stars, you would have to place that telescope in space. And so we have this X-ray telescopes. One of the most famous is the Chandra X-ray Observatory. Why will the rotation of a star increase as it collapses? And you think about the Great Collapse. We're talking about this huge iron core that collapses in a second. And even if it was spinning very slowly in the beginning, because it's so small now, due to conservation of angular momentum, neutron stars can rotate anywhere from 10 to 1,000 times every second. Okay, and it goes back to what we talked about, where if, let's say, you have an ice skater who's spinning and she has her arms out, and then she pulls her arms in, she's been spinning faster because of conservation of angular momentum. Remember, her angular momentum doesn't change. It's just that since her moment of inertia gets smaller, her angular velocity increases. Look at this picture. Where is the magnetic field strongest in this picture? And if you want, you can pause and think about that. And hopefully you'll realize that the magnetic field lines are closest together where the magnetic field is strongest. And it turns out that neutron stars have magnetic fields up to 1 trillion times larger or stronger than the sun's magnetic field. What would happen if two neutron stars collided? and basically you would, you would obviously exceed that 3 solar mass limit, and even at that point, if now that you're above 3 solar masses, um, it would be impossible for even the neutron degeneracy pressure to hold the star to withstand the gravitational force. And in that case, we would get a black hole, which we'll be talking about soon. Okay, so by the way, I was going to show you a video if we were in class, but I'll just link that video onto the bottom of the assignment there. You can watch that. It's a pretty interesting video about neutron stars. Here's some summary questions to discuss with your homies. I would suggest that maybe you post your answers to this on the in the comments of the of the Google Classroom page there, and there's actually one, at least one of these questions is in your homework as well. Okay, so I hope you enjoyed this lesson as much as I did, and I hope you will have a fantastic rest of your day, and I will see you guys very soon.